Ready.
Because then I will start. Okay, so hello and welcome to our 2 days webinar organized within the VicInAqua project with the title Turning Water and Energy Challenges into Opportunities. I'm quite happy to have you all here. My name is Carsten Bolz from Steinbeis, one of the project partners. And I'm happy to introduce you today our speakers who are Professor Dr. Jan Heunkes from the University of Applied Science in Karlsruhe. He is the coordinator of the project. And I'm also happy to introduce Kira Hovanas, who is with us today. She's from Aqua Biotech, and they're a senior consultant for aquaculture development. So welcome to our webinar today. Thank you for sharing your expertise with us. And yeah, so I would say let's start. But before I introduce you to the agenda, I just would like to raise your awareness to get involved with us as a project team. So please feel free to join our stakeholder community on the website, subscribe to our newsletter, follow us on LinkedIn, Twitter, and Facebook, or just go to the website and drop us a message if you want some more information on the project and connect with us. I would like to start with the agenda so you know what you can expect today. Before we jump into the actual project and have a look at the different technologies, I first would like to give a short introduction on water and energy challenges. Then we will go into the specific case of the VicInAqua project, and then there we will have a short project overview. And then we will go through the different technologies which are applied within the project, which are the membrane bioreactor, the monitoring and control system, the recirculating aquaculture system, as well as the renewable energy supply systems. And after that, we will have a more general presentation about the integrative approach and to address the water and energy challenges and to explore opportunities. And afterwards, after the presentation, we would also like to have a question and answer session. So please feel free to use the webinar also to ask your questions. On the bottom right, you can see the chat function, and there's a little question mark icon. So if you have a question, just click on the icon, ask your question, and then we will feed your question into the question and answer section at the end of the webinar. So you can ask questions whenever you want, but we will pick them up then in the question and answer section. So as I said, let me talk a little bit about the water and energy challenges in general, and then let's have a look how this how the VicInAqua project fits into these kind of challenges. So first of all, I mean, water and energy challenges are mainly global challenges, and I mean there is a growing water demand, and we all know about water scarcity. This is, I mean, one part as well of the VicInAqua project, but the VicInAqua project mainly addresses the water pollution which takes place at the Lake Victoria Sea. So there is also insufficient access to sanitation, which is another quite large challenge, which is also addressed within the project. When we have a look at the energy challenges, the main challenges which are addressed by the project is the unreliable energy supply. So the VicInAqua project uses renewable energies to kind of provide reliable energy for the system mainly. However, I mean these global challenges are on a broad scale. I mean, these appear in various countries, in various regions. It affects the population. And however, one could state that there's unfortunately not a silver bullet solution which kind of fixes all these kind of challenges, but there are ways one can help to meet these world's water and energy challenges. And this is exactly where the VicInAqua project kind of approach these issues. And because it's a research project to develop and integrate new technologies addressing both water and energy challenges, and to draw key learnings on how such technologies can be made available in environments such as in Kenya. So it's just like compared to the scope of the challenges, it's kind of one approach of how to address these challenges in a sustainable way. So now I want to hand over to Professor Hoinkes, who will give an introduction to the VicInAqua project.
Good afternoon, everybody. Thank you, Karsten, for the introduction. As Karsten already mentioned, I will continue with giving you more details on the technologies which we employed in the project. And I will start also with a more specific overview. So with the next slide, as already mentioned, the Lake Victoria region is our target area. And as in many other areas in Africa and elsewhere, there are the typical problems of our times, like high population density, urbanization, high rate of poverty. Fish processing industry is growing. So there was a flourishing fish industry previously. However, as you could see, overfishing is a big issue. So the people started to complain that there's lack of fish nowadays, and the fish is coming even from China to get processed in the local industry, and this is a very big problem. That there's not enough fish to provide food to the local population. High wastewater discharge. In many cases without any treatment. So if there was any treatment, it's not the quality or the efficiency of treatment is not good enough. And there's also a lack of awareness on the environmental issues and environmental impact. The photo at the bottom shows you what is striking when you enter the lake, the shore of the lake, that many times it looks greenish. And this is due to the so-called water hyacinth. This is a weed, aquatic weed, and this shows the eutrophication or the over-fertilization of the lake. Okay, what is our vision? Basically, I'm coming to details later, as already mentioned. Just quickly, we want to develop a multi-purpose self-cleaning water filtration solution for sanitation and for providing water, fresh water, to the aquaculture system and for irrigation as well. We want to train capacity building the local actors and train students as well. And so a special focus is, of course, on the robustness and the energy efficiency. And very, very important, this is always probably one of the biggest challenges in these projects, to make it economic viable. So to provide a solution which is affordable by the local population. And okay, novel solutions, innovation is always very welcome. And I'm going to present you this in the following. Okay, before I start with the technology, let's have a look on the partners. It's a well-balanced consortium of European partners from Germany, Italy, Malta, and African partners as well. These partners are all situated around the Lake Victoria, in Kenya, in Uganda, and in Tanzania. You can see the particular partners around. So we are 11 partners in total. And okay, what are the main objectives? As already mentioned, membranes for cleaning, for treatment of the water, and we are opting for self-cleaning, a novel membrane, type of membrane, which hopefully needs less cleaning, or hopefully no cleaning chemicals at all. So this is to be shown. And membrane bioreactor is another keyword. So with the next slide, I will show you what this is, combination of membranes and bioreactor. Renewable energies, PV, biogas, real-time sensor system, remote control system to ensure a smooth operation of the system. And of course, the assessment of in terms of socioeconomic studies, very, very important, environmental impacts. Awareness raising, we had already within the project a lot of training sessions and roundtable discussions, and last but not least, to foster the gender, so women is a special focus of the project as well. Okay, this is just a very rough overview, so to show you that we can transfer technology, new innovative technology from Europe, from our developed countries. However, we do need this by regarding the socioeconomic aspects, and this input comes from our African partners. Very important to listen to their requirements and to their needs. So this gives you the balance of the project. Okay, now coming more detail to the technologies. This is the overview on the system, the approach, the project approach. In the center on the right hand, you could see the Wrasse. This is the recirculating aquaculture system. This is a aquaculture system with almost 100% of recirculating of the water, a closed system. So the system does not do any harm to the lake or to the environment. It's supposed to be, as I said, almost completely closed. However, there is some water loss due to backflushing of the filters, due to evaporation and so on. Therefore, we have to refill the system every once in a while. And this is done not by fresh water, however, by treated wastewater, domestic wastewater, industrial wastewater from fish industry. And this wastewater passes the so-called membrane bioreactor, details coming later. And the quality of this drain of this effluent is good enough to replace the water, the water loss in the Wrasse. The system is powered by renewable energies. So all this, the MBR plus the Wrasse, all the sensors, and the degree of autonomy is based on the experience so far, 40 to 50%. But I'm coming to this also later in the final part. As mentioned, an online monitoring system by online real-time sensors, and some part of the water is also used for irrigation. In the following, we'll show you some nice photos of our little field where we grow some vegetable as an example to see how the quality of the water affects the growth of the crop. Okay, membrane bioreactor. It's nothing really new. So throughout the last 15, 20 years, there were many publications on this, and many large-scale, full-scale units running worldwide. In Africa, it's rather new. So it's not what I want to show you, a really complex technology. It's rather simple. However, you need to train to make the people aware what it is. It's a combination of the existing activated sludge process, what is employed in the typical sewage treatment plant everywhere worldwide, and it's combined with membranes. What is the benefit of this? Finally, you do not need the settling tank. You can cancel the settling tank, and you do not need any further disinfection. You just pass the treated water through the membranes. And there are actually two systems with a side stream or with submerged membranes. On the left-hand side, you can see our actual membrane bioreactor with the 3 chambers. And in one of the chambers, on the left hand, you could see the membrane module. And by sucking out, the membrane module is submerged in the biosludge, in the activated sludge, and by a suction pump, the treated water can be drained and can be used for the purposes already mentioned. And the most salient feature of the MBR is that it's very compact and the outstanding water quality. So it's perfectly suited for reuse. So it's significantly reduced in germs, almost nothing, 99.9% be reduced, and a very, very compact system. Okay, this slide gives you an impression of the installed MBR at the site in Kisumu. On the very left, you can see the influent, the pump, the feed pump. It's in the backside, so underneath this blue sky, you could see our pilot plant, the white one with the white rooftop, and it's roughly 200 meters away from our point of entrance, and we have to pump the water to a feed tank. This is the next right on the right side. The black tank. This is the feed tank. It's situated at the pilot site, and from the feed tank, it's fed into the MBR. And the other three slides give you an impression how it looks like. And at the bottom, you could see the water quality, the inflowing. So the wastewater, this black brownish water, and on the right side, you could see the clear and light water, which was treated by the MBR. So we have experience with this MBR since last December we started, so roughly 4 to 5 months. It's running smoothly. There were some, it's usually, as you know, there are some technical slight problems, but basically it's running fine. We are very satisfied with the quality. We started to feed it to the aquaculture system and for irrigation. And one thing, just the final line, additionally to the membrane, we have an UV lamp. So we have two systems to improve the hygienic situation of the waters, and membrane should be enough. But if there's any problem with this, we have a UV lamp, which could be also used to kill the potential germs. So with the next slide, you can see some details of the first phase of the installation and commissioning of the MBR. We had the pre-filtration is very important. It should be a millimeter scale mesh, and we played with two versions, 1 and 2 millimeter. And we had another pre-filter, which has a smaller mesh size. And so what is also important is that every once in a while, these MBRs have a trend to foam up due to the stress of the bacteria if the load is too high. And but this can be controlled very well by anti-foaming agent. And you have to see by naked eye how the system develops and give some drop of anti-foaming agent. But this is only in the initial phase. In the acclimation phase, later, if it's fully acclimated, it won't foam anymore. So one thing, in general, MBR, there are many membrane suppliers now. We have a German MBR membrane supplier, UF membranes, ultrafiltration membranes, and there are many more in US, in China, and Korea. And one of the scientific goals of our project is to develop novel low fouling membranes. So the problem with these already existing commercial membranes is that they have a fouling propensity. So what does it mean? Particles or some organics or biofilms will be stuck on the membrane, will reduce the flow on the flux of the water, and will reduce the efficiency and driving the cost up. Therefore, one of the scientific goals of this project is to develop novel anti-fouling coatings on top, which can be coated on top of the existing membranes. I don't want to give you too much details. On the website and in this newsletter, you can find more. So just on the right hand, just to give you a visual impression how it looks like. So The very top there, this dark brown, this is the commercial membrane. This was treated with a model foulant, and underneath this commercial membrane, you can see our PBM-coated, the novel-coated membrane, which is much lighter. This shows that we have less fouling. And so there are many, we have a PhD student involved. There are many other investigations which were carried out on to study the materials and so on. And so just one information on this. Last month, at the beginning of April, we started to replace part of the membranes in our MBR, and the real one, and the pilot scale one in Kenya, by the novel membrane. So we are running currently the commercial and compare it with a PBM coated. And we hope, so at the moment we have not fully studied this. After some weeks, we want to see how the system develops, and hopefully to see that our novel coated membranes perform better than the actual ones. Okay, so I can now pass the floor to Kira to continue with the Wrasse system.
Yes, thank you, Jan. Good afternoon, everyone. Thanks for joining our webinar. So my name is Kira. I'm an aquaculture consultant at the AquaBiotech Group in Malta. And the AquaBiotech Group is a national consultancy and engineering company focused on aquaculture. So we're doing any projects that have to do with aquaculture. And one of our projects we're working on is the VicInAqua project. So we were in charge of designing and constructing the recirculating aquaculture systems, which I will tell you a little bit more about now. The project is a pilot project. So we designed a small tilapia hatchery. Initially, it was the idea in the proposal to just have a showcase fish tank to show that the MBR water is clean enough to use for aquaculture. But we wanted to do something bigger, that we can also promote aquaculture in the countries around Lake Victoria and show the technology is available. So therefore, we decided to opt for a small tilapia hatchery, because according to our local partners, tilapia was the main fish on the market, and they were in need of fingerlings. So in the end, the tilapia hatchery will be run by our partners in Kenya from Kisumu County, the Department of Fisheries, and they will use it as a training and demonstration facility, and of course they will produce fingerlings for the local farmers. They can produce, the capacity of the hatchery is around 25,000 fingerlings per month, 1 to 2 grams. Depends, we're just starting, so we have to see how well the growth is and how they are doing with that. So as Jan already mentioned, the recirculating aquaculture system is a system that has filtration system within the system. So we're recirculating the water around normally 90 to 95% of water on a daily basis is recycled. So that water that we need to top up is coming from the MBR. So we size the system of the aquaculture and the MBR together, so that we have every day we have enough water to top up the aquaculture system. The water that goes out of the Wrasse, except for the evaporation, goes back into the MBR, and the solids are going to either to the digester, the biodigester. We have also biogas in the project, which Jan will talk about later, or it goes as a fertilizer on the agriculture field. One of the goals of the local partner is also to test. They will grow out some of the fingerlings that we produce in the hatchery, and they want to see if there's any residues of heavy metals or pathogens after they grow it out in their tanks. On the next slide, you can see the hatchery, render of the hatchery. So we have 3 systems, 3 recirculating aquaculture systems. So we have there we have the broodstock. So this is the parent fish. We have females and males. And some of the tanks are used as conditioning, and some of the tanks are used for spawning. And we also have a small egg incubation unit, which you can see in black on a small table. So we collect the eggs from the females once a week, and then we incubate them in the egg incubator. And then on the top, you can see the larval rearing system and the nursery system. So from the egg incubation, they go to the larval rearing system, and then from there, they go to the nursery. In the larval rearing session, they are treated with hormones to produce all male fingerlings, which is more beneficial to the fish farmers because all male grow faster and they all grow uniform. If you stock mixed sex tilapia, then in the ponds, then the fish will interbreed and you'll end up with different sizes, which is less efficient for production. In the middle of all these systems, you see the filtration systems. I will explain to you more about this in the next slide. So all these systems, they consist of obviously fish tanks, if we start at the fish tanks. And then from the fish tanks, the outlet water goes to a drum filter. This is a mechanical filter that filters out the largest solids and also fine solids. It's a rotating screen, and every few minutes it is a backwash. So then the sludge, the dirt will go out, and the clean water will continue to the biofilter. So this is what Jan was talking about the backwash, that we lose water because we spray water on the screen to clean the screen, basically. So this we have to top it up with new water every day. In the biofilter, there is ammonia is transferred to nitrate, and then from there on, it goes to a pump. So the pump is ensuring that the water is recirculated in the system. It goes to two ways. It goes through a protein skimmer back to the biofilter, and it's pumped up to the header tank. The protein skimmer removes fine solids and dissolved solids. Then from the header tank, this is just where we provide aeration to the water, so oxygen with air blowers. And from there, with gravity, it goes through a UV back to the fish tanks. So the water runs around like this all day. I'll show you some pictures of the actual system. So on the top left, you can see from the roof of the VicInAqua pilot, you can look into the greenhouse because the whole hatchery, to keep costs low, is made in a greenhouse. So those big tanks are the broodstock tanks. Then on the top right, you can see inside the greenhouse, you can see one of the filtration systems with the header tank, the protein skimmer in front, the gray circular conical thing. That's the protein skimmer. Then you can see the biological filter, which is the white tank inside of under the ground. In the front is the drum filter, and on the back you can see the different tanks. Left down is the broodstock system, and then on the bottom right you can see one of my colleagues giving training to some fish farmers and local government on the systems. Here you have the operation of the aquaculture system. So the first picture is of stocking the broodstock, and then on the top right you can see the broodstock tanks. So we use nets for the breeders that are spawning, so you can easily manage them. So you can put the net to one side of the tank to check the females if they have eggs. If they have eggs, you harvest the eggs from the mouths, tilapia mouth breeders, and then they stock this in the egg incubation, which you can see in the bottom. So they stock it first in these, we call them McDonald's jars, and then once the eggs hatch, then the swim-up fries, they go automatically to the top, and then they go into a tray, which you can see on the right. So there the fry are there, and then once they are ready for feeding, they are transferred into the larvae system. As Jan mentioned, or Carsten, all of this is monitored by a monitoring system. This is designed and installed by our partner Oxygard from Denmark, and they are specialized in designing monitoring and control systems for aquaculture all over the world. So what this does is every fish tank has a probe. So this is a measuring device which can measure temperature, pH, oxygen, redox, to gas pressure. They can basically measure anything. For VicInAqua, we have used only pH, temperature, and DO. We also have a system in the MBR, so a probe in the MBR. So this system is also monitoring the water quality in the MBR. It's also used to control emergency oxygen, because in Africa we have a lot of power outage. Even if we have solar and biogas renewables, we always need backup of backup. So we installed an emergency oxygen system using medical oxygen cylinders. And once the oxygen gets too low in the tanks, which is monitored by the system, then emergency oxygen will flow into the tanks to make sure that the fish always have enough oxygen. So these readings can be, so these probes are connected to a box, which you can see in the middle picture. So in the system itself, you can always, anytime, read the temperature, the DO, and the pH, but you can also read it from a mobile phone, from a computer, from anywhere, basically. So, and on the left, you can see the power supplies of all these probes. And for VicInAqua, Oxygard has developed a special product called Nautilus, because they want to have a low-cost, robust management system. They also want to include some of the management of the hatchery, which is fish feeding, and things like that, so they can put in how much fish they fed, but they're not using this yet. It's still under development. Here you can see some of the interface. So this is what you would see on your phone or on your computer. So you can see the fish tanks with all the readings inside. On the right, you can see our hatchery manager in the control room. Yeah, and also you can always find the data from the previous months, because it's all stored in the system. And they also have alarms. So if in case the technicians are not on site, it can be connected to their mobile phones, and they get an SMS or a call when there's a problem. So they can go to the site and fix it. So this is about the Wrasse and the monitoring and control system. And now I'll go back to Jan for the renewable energy.
Oh, thank you, Kira. Okay, Nico. Yeah. First of all, I would like to introduce the PV solar system. It's a 15 kilowatt peak system. And in addition, we have also installed a 30 kilowatt hour battery or accumulator, lithium-based. And so at the bottom, you could see, give you an idea of how the panels look like. And on the top right, you can see the control room with the black down boxes. These are the batteries, 3 batteries, 10 kilowatt hours each. And our strategy, as already mentioned by Kira, is mainly to get power outages, which happens frequently, almost every day. Half an hour up to several hours, and this is the main idea of the system. We do not provide full autonomous system. This was by far too expensive. So based on the previous experience so far, we installed the system last year in November, and by then we are running it through all these seasons, and so far we can provide 40 to 50% of the total energy. So this means the pilot is connected to the grid, and the rest of the energy is supplied by the grid. And there are many details about this, but just one thing I would like to mention: during daytime, when there was sunny light, we can provide almost everything, so 100% of the system. However, in the night, we do not discharge the batteries too low, just 30 to 40%, in order to keep a reserve in case that there was a power outage in the night. So we always keep part of the capacity to be prepared for this. So in addition, we have a generator, and I'm coming later to the biogas generator, diesel generator, and we also can supply oxygen, pure oxygen to the fish, as already mentioned. Okay, this is information, these slides, and the text giving you information on the biogas system. So in the middle, on top, you could see these black bags blown up. We feed agricultural waste and cow dung, and this produces the biogas. The biogas production rate is about 10 cubic meters per day. And what else is important? We pass the produced biogas in order to remove CO2, to increase the methane ratio. And we also need to remove some kind of contaminants like sulfur compounds, and to remove humidity. And this biogas is stored in a big tank, and it's fed into a biogas generator. And in addition, we have a system which I'm going to explain later in the following, a so-called thermoelectric generator, in order to tap more energy to increase the efficiency. So with the next slide. This gives you an idea what is a thermoelectric generator. It's nothing else but a kind of material which taps heat, which has a hot side and a cool side. The cool side is the ambient, typically, could be water, air, and by doing so, it produces electric energy. On the left hand, this graph shows you results of a laboratory experiment with some of these TEG materials. And the higher the temperature, the more you move up with the temperature, the higher the power will be. As you could see on the y-axis, 50 watt in this case, 40 to 50 watt when we go above 200 degrees Celsius. So this effect is rather well known for very long. It's called the Seebeck effect. And so what is new is so far this technology was only used for space technology, where the cost doesn't play a role. But nowadays there are new cheaper materials coming to the market, and now it's going to be interesting to use any waste heat. The efficiency, when it comes to efficiency, is not too high. It's just like 5 to 7%. However, the good thing is you have no moving parts. It's just a block of materials, and therefore the lifespan is rather long, 10, 20 years, and you do not need to take care for any maintenance. Okay, we make use of this TEG technology in two ways. On the right hand, as already mentioned, we use it to pass the exhaust gas of the biogas generator in order to tap the waste air of the generator. This is our high temperature device, and so around 200 to 300 degrees Celsius. We have installed a small pilot with the max energy of the TEG 300 to 400 watts. It's not too much. However, we just want to show how it works. And this is the first time that we get any experiences. I think in Africa, this has never been used. And therefore, we started with a smaller system. On the left-hand side, you could see that we also make use of this TEG technology to harvest some additional energy from the photovoltaic panels. As you may know, photovoltaic panel at higher elevated temperature lose efficiency, and therefore the TEG is meant to cool and to tap this extra heat, to produce more energy, 10 to 15% increase in total energy. And with the next slide, you could see on the left hand at the bottom, these white spots, these are our TEG elements on the backside of the PV panel. One version, what we tried out was to put it on a floating cooling fin, aluminium cooling fin, and this is the photo in the middle, cooling and swimming on top. This could be used, for instance, to put it on the ponds. And so there are two benefits. We cool the system, so temperature will be reduced, efficiency of the PV will be increased. And on the other hand, we could use this cool and this hot or warm side for energy production with the TEG. On the right-hand side, we also installed this PV TEG module with an air cooling and integrated in the existing PV system on the rooftop. And this is still running. These four nice photos give you an impression of our little garden, our experimental vegetable field, which is irrigated by the water from the MBR. And so don't ask me about details. These are any typical local vegetables. So, okay, these were the technologies quickly. And coming back to the integrative approach, again, as I started with, our general approach with the Wrasse system, the recirculation system, and the MBR to feed the treated, the clean water. I showed you some aspects of the renewable energy system, solar and biogas. Kira explained about the online monitoring system. And these final images showed you our use in agriculture, so irrigation in agriculture. Okay, on the left-hand side, again, there is an overview on the pilot plant, and the backside. These are the Wrasse tunnels. The part with the rooftop. On the rooftop, we have mounted the PV panels. And there is on the left side, the room for the MBR inside this, under the rooftop. In the middle, there is a small office as well, and a room for making water analysis, and then a storage room as well. On the right hand, as you have already seen, is the Wrasse system with some of these tanks. Right in the middle, this is the MBR, one of the deputy governors of this Kisumu state around the lake, in the Lake Victoria region, visited in the inauguration. And this is the guy with the red tie. And down there you could see the Maasai who celebrated with us the inauguration. They are in charge of taking care of security at the site. Okay, this is this is like a map showing you the situation. Again, I started with this, probably was a bit too quick, and as we mentioned, we set up left-hand side the VicInAqua pilot plant next to the already existing wastewater ponds, and you could see the wastewater in-tank, and we have this intake line from the wastewater in-tank to our pilot plant. So, and by the way, these ponds, these waste ponds, is a typical African version of these ponds with the anaerobic part and aerobic part and so on. And at the bottom left of this pond, you could see the outlet, which is for discharging the treated water into the Lake Victoria. And on the right hand, you could see the mechanical core screen, already existing intake sump, anaerobic pond, maturation, just to give you an impression. So it's nothing with our pilot. It's just the, and finally, the impacts, coming to the impacts, we have shown that the MBR can give an effective sanitation, very well suited wastewater treatment for treating the water to be reused in the Wrasse and for irrigation. And we avoid the release of fertilizers, a closed system, and antibiotics, and what might be difficult in the aquaculture. So we want to run a so-called bio system with less use or no use of any chemicals. This is one of our aims. We make use of a variety of renewable energies, so we could lower the CO2 footprint. And the degree, as I mentioned, of autonomy is 40 to 50%. So it also contributes to lower the overall energy operating costs. We have an assessment. We are still about in the final phase to make an assessment of the environmental impact, very important, a life cycle analysis. And we used the system to provide a sustainable and environmental friendly solution. And so we could also remove parts of the fertilizers in irrigation. By the way, our MBR is flexible. This is one of the details. We could also denitrify with a denitrifying unit, so we could adjust the level of N. So if needed, we could go for higher N in irrigation. We could lower this, which is important for the Wrasse system. So we are also flexible in this regard. And of course, finally, want to increase the fish production, productivity, and to make a business with these fingerlings, which are to be sold to the neighboring companies. There are many fish farms around in the Lake Victoria, which have great demand for these small fingerlings. Okay, for the society, we contributed to raising awareness. So we had many trainings, many visits of the plant, and which is ongoing even after the end of the project. We want to keep it as a training unit and an awareness raising unit in future as well. It's an integrated or integral technical solution. What needs to be shown for sure in future is the economic benefit. So at the moment, we have invested the EU-funded money, which was by far not based so far on an economic base. So it was meant to show the viability of the system, very important, and to see that it works. Now, finally, at the end of the project, we have to make a economic study of this. How is the economic viability? And our next step is, by end of the project, to design a so-called, I always call it low-cost version, which is something which could be brought to the market to replicate this technology for the next step. This is one of our homeworks we have to do. And last but not least, encouraging women. There are many women already involved in the aquaculture, what we learned, and to further strengthen this. Okay, so with the next slide, I will pass to Kira. She will report on the potential markets in this area.
Okay, thank you, Jan. So I already saw someone asking why we chose tilapia for this project. Tilapia is the most popular fish in the area. That's why and then second is African catfish. So we asked our local partners in Kenya to do a market research at the beginning of the project, and they found that there's a big need for tilapia fingerlings in the area for the farmers, because they only have low quality fingerlings. For example, mixed eggs, they don't grow well, so they wanted us to focus on tilapia. However, the Wrasse is also suitable for other species. They already have done some experiments with African catfish in the hatchery, but they could also use it for other species like Nile perch. There's other species being eaten in the area like silverfish, lungfish, and Nile perch. Maybe sound logical. Around the lake, the people are very dependent on fish as a protein source. They're used to eat these fish. The price of tilapia depends on the size. Should be around 3 to 5 euro per kilo. The market size fish. Some problems that they have there is that there is no cold chain in the production, meaning that to once the fish is harvested, to keep them in a low temperature to avoid contamination of microbes and chemical hazards, things like this. So therefore, they have a lot of frozen tilapia coming from China. This has been the norm that they eat there. However, the government now has banned this fish from China to give the chance to local farmers, because to compete with this low price tilapia from China is very hard. It's not fully implemented yet. You can still see a lot of tilapia from China on the market. It needs to be enforced, but the start is there. Then for the Wrasse, because Wrasse is quite an expensive technology. Fish ponds is much cheaper to run usually, so I wouldn't recommend to use the Wrasse for grow out tilapia if there's plenty of land for ponds, for example. We promote Wrasse for example, urban aquaculture, where they don't have a lot of land available and they don't have a lot of clean water source available. So in larger volumes, you're close to the market. This could be financially viable to use Wrasse there, and for hatchery productions. So to raise high quality fingerlings in good quality water. It's easy to manage. It's easy to do the sex reversal in tanks. So we promote the Wrasse for these purposes. And then back to Jan again. I will answer the rest of the questions in the question and answer session.
Okay, thank you, Kira. So, finally, what were the key learnings of our today's webinar? Fingerlings with high quality are very relevant in the Lake Victoria region. There's a high interest in the project, so many people around the Lake Victoria are coming, visiting, and contacting us, waiting for the commercial part of the project to see how real market product, we are not so far yet, how it looks like, how about the cost, of course. So the key players, governmental institutions are very willing to support scale up. It's always like cultural differences are a challenge. So we still need more training to make the people aware, to make the people familiar with the technology. This is still ongoing, and therefore we keep our pilot at the end of the project for this purpose, in order to train people. This will be finally in charge with the Ministry of Agriculture and Fisheries. They will be in charge to continue with this at the end of the project. Training is always needed. When it comes to financial sustainability, we still have to do our homework, as I said, to develop a low cost and to see in the final how far we can get in terms of economic viability and energy supply. This is the first step. What we learned, the lesson learned is it's in terms of economic viability. It's good to be connected to the grid, but this can be easily done at the sites, at the ponds, and so on. However, it also makes sense to provide part of the energy by renewable energies, and as I mentioned, in particular, to get the power outage. It's very, very important to run the system smoothly.
Okay, so thank you, Jan. Thank you, Kira, for the presentations, for all the insights. And I would like to take the opportunity to start our question and answer session now. There are quite a lot of answers asked from you. We're very happy to answer those. And I would like to start with the first one, which is about the membranes, which you can see here. Is the self-cleaning feature of membranes scalable to other membranes filtering air, for instance? So I think this is the answer to the question to you.
We are fully concentrating on water membranes, on water filtering. We have, to be honest, no experience with filtering air, so I cannot give any answer to this. So no experience with this.
Maybe I also want to pick up another question we got asked quite a lot with regard to the membranes, and this is about the lifetime. What is the expected lifetime of the membranes used in the project?
Yeah, based on the previous experience, worldwide, the lifetime is for years, so it depends a bit on the quality of the water. However, this domestic wastewater is like a less problematic wastewater, put it like this, and we can expect lifetime 5 years plus X. So sometimes people run it for 10 years, so before replacement. So it's for very long time. It's meant for very long time. What we don't know is about our novel coating. This needs to be studied for sure, because we put an anti-fouling coating on top, and this is what has to be shown. How long is this lifespan of this? We don't know at the moment.
And with the membranes, do you need to replace them, or can you clean them when they are kind of?
So number one, we can clean them. So we did it already. So one of the membrane packages was already blocked at the beginning. Was that because there was a stop of the water supply and so on? No details. And we used chemicals like hypochlorite for this purpose. And this is a chemical, of course, we want to avoid in order to reduce the cost, to reduce the complexity of the system. However, the chemical is available on the local market, and it's not too high in cost. This could be done, and we'll see in the following with our membrane, the new one, and the commercial one, which needs less cleaning in the long term.
Okay, thank you. Then I would like to. We have several questions to the Wrasse system, and I would like to just ask you, Kira, to answer the first one, which is in terms of cost efficiency. The tanks were made locally. Are they fiberglass or cement?
Yes. So we try to use as much as we could local materials. We were designing the system when we were still in Malta. So some of the things we were not able to get locally because we didn't have the contacts yet there, the contacts. So the smaller tanks are local. They're from Nairobi, but you can get them all over the country there. These are the larvae and nursery tanks, the round black ones. They're very cheap and very local. And then the fiberglass tanks, we took them from Malta because at that time we didn't have a contact in Kenya, and we wanted to show, because cement tanks they have already there, so we want to show new technology. So we decided to take the fiberglass, but by now we have a contact there, so it's possible to get the fiberglass even in Kenya, and they're about the same price as cement. So in that case, if you choose for cement, you would spend the same. However, for these large tanks, for the broodstock, we found that really if you want to make something for Africa that's financially feasible, we would put the broodstock in ponds if it's a big hatchery, because that's it's cheaper in the end. I hope that answers your question, Hugo.
Thank you, Kira. I just want to come to another question from Hugo, which is also related to the Wrasse, and this is: how do you deal with an O2 alert? Do you have oxygen bottles in stock, introduce new water in system, or other measures?
Yes, so as I said, we have medical oxygen bottles as an emergency oxygen. So this is connected to the monitoring control system. So once the oxygen gets too low, you can set the threshold yourself. You can change it as well. So if it gets below the threshold you put in the system, then automatically emergency oxygen will flow into the tanks where the oxygen is too low. And then the alerts to going to the technicians at night, for example. If there's really a problem, like even if this doesn't work or if the oxygen tank is empty, which it shouldn't be, but you never know, it's still Africa, then they can indeed exchange the water. If there's not enough water from the MBR, they also connect it to the main water supply in case of emergency for water exchange.
Okay. Thank you, Kira. And then I have two questions with regard to the feed of the Wrasse. So the first one is, are you using Wrasse feeds to minimize the impact of the effluent water on the surroundings?
Wrasse feeds, you mean, I guess he means feeds specifically designed for Wrasse. We don't use those because they are not available yet. I think it's really hard to find them anywhere, but in Africa for sure not. So we use local tilapia feeds, pellet feeds. We don't have any impact on the effluent water because we don't have any water going into the environment, since the water that comes out of the system either goes back into the MBR or it goes onto the agricultural field, and the sludge as well. It goes into the agricultural field or in the biogas digester.
Okay, and I think you already answered that question as well, which was what type of feed are you using for feeding the tilapia? From where is the feed to reduce feed cost?
So we use commercial feeds because but sometimes they might seem more expensive than like farm-made feeds or single ingredients. However, these are specifically developed for the tilapia, so they like maybe per kilo they are more expensive, but in the end, because the feed conversion ratio is much lower, in the end, it's not more expensive than like not very good quality feeds, because the fish grow much faster.
Yeah.
I hope that.
So
here, I don't know.
Thank you. Talking of costs, there was also the questions with regard to the Wrasse system. What is the estimate amount or the estimate cost, I guess, for the Wrasse system?
So for the Wrasse we have in VicInAqua, as Jan said, this is a research project. So we put everything there to test, basically. So the idea now of the last task of this project is to design an upscaled system, so larger volume, that is financial feasible. So I can tell you the price of the cost of this system, but it doesn't really matter because it's a research project. It's not the commercial price. We didn't include the man-hour cost and things like this, so it's basically useless. But yeah, if we finish our project, which should be it's by the end of May, and then the reports will be in the end of July, then I think the deliverables will be publicly available and you can have a look there. Or if you send us your email address, we can share it with you. Because we're doing economic analysis, and all the information you can find on this project will be in the deliverable. Or you can send me an email if you have a specific Wrasse ID that you would like to know the cost. If you want to actually build something, then you can always contact us.
Thank you, Kira. I want to now go to a question which is a I find it very interesting one, because we were also elaborating on that while we started the project. And this is, can't the water hyacinth be used in the biogas reactor to minimize the risk of power outages?
Very good question. Yeah. Okay. At the beginning, we thought of this because it's well known, and there are many publications that water hyacinth can be used for biogas. However, one of our partners in Africa, he refrained from this because he told us that we cannot ensure water hyacinth supply for the entire period. So it depends a bit on the season, harvesting the water hyacinth at the lake from the surface of the Lake Victoria. Sometimes it depends a bit on the wind. I did not study this. I just followed this advice of our local partner. and therefore we refrained. We stayed away of using this water hyacinth. However, when I was last time in Kisumu in a conference on environmental technologies in general, this was in February this year, and there was a company, they make use of the water hyacinth. They produce bricks of the water hyacinth, which is also very interesting, and it raised a high interest in the audience. So they harvest the water hyacinth, they dry it somehow, they compress it and provide it bricks to which can be used for incineration, for running an oven and so on. It's a very hot topic and a very good idea to make use of the water hyacinth. So, but I haven't seen a biogas project so far.
Can I add to this? Can I add something to this? Because yeah, all these projects that we saw at the conference, they are all by the lake. And what was also a problem for us is, even if we could harvest them all year around, we were not allowed to, because it's a highly invasive species. So it's not allowed. You were not allowed to transport it. And since our site is not on the lake, we could not get the hyacinth from the lake to our site. Maybe if we would have to go through a whole permit system, then yes. But for a short-term project, this was not very viable. That was the second reason.
Okay, thank you.
Thank you. I just want to go shortly back to the general, because there was a question about the tilapia. If you could please elaborate a bit about the monosex tilapia culture.
Yeah, I don't really know what the question is here.
I think the main question is why do you try only to grow a monosex tilapia culture within the Wrasse system?
Yeah, because I already.
Or in general for aquaculture.
So because monosex is all male tilapia. So in the hatchery, you make sure that all the fingerlings are male. You do this because they grow faster, males than females, and also then you will have a uniform growth, because they will all grow at the same speed. If you have mixed sex tilapia, the tilapia get mature very early. So they start breeding in the pond. So first of all, the females, they will not put their energy in growing, but at reproducing. So it's not very efficient if you want to produce tilapia for the market. And as well, you will have a lot of different sizes of fish in your pond, which is not efficient for production as well, because you give the feed specifically for the fish in your pond. So if you have different sizes, you have to give different type of feeds. You have different growth of different fish. You even have small fish that need specific feed. So that's why, in general, monosex is the way to go with commercial farming.
Thank you, Kira.
Does it make sense?
I have two more questions on my list, which are mainly questions we also got asked quite a lot, which kind of refer to the overall project. So one question is, how many persons do you need to run the system, to take care of it, to maintain it? Because it seems there are a lot of technologies, but how many, is it a huge effort to run it?
Yeah, again, it's just a pilot and experimental site, a living lab, so to say. And so at the moment, we have two technicians, two persons who support the work on this site. However, we have a lot of different technologies, it's not optimized, the system. We have PV and we have the MBR, and finally you have to see with the low cost, the large scale, what we really need. Yeah, Kira?
We also have some interns on the pilot that help the technicians, and we also have someone to take care of the vegetable garden from our local partner. So the technicians don't have to work on the vegetable part. The technicians, they take care of the Wrasse and the MBR and the renewable energy, I would say. But when it's time for harvesting, and then they need an additional person.
But in general, when we talk about the system, when it's like on on a normal day and it runs like normally, it's enough to have 2 technicians there to run the whole system in the end.
I think so. Yeah, I think so. Yeah,
roughly.
We could. Yeah.
So, and I would like to kind of close the question and answer session with kind of an outlook. So I'd like to ask you if you think about, okay, what's your vision for the pilot side, which is there in Kisumu at the moment? What's the vision, and how is the also how is the opinion of the local community there about the pilot side?
I think number one, we have to keep it ongoing. The pilot as a living lab, as a demonstration, as a training facility. Number one, to show people, to train people. And as we mentioned, Kira and me, we need to go for a larger upscaled version with lower costs. This is the next which might be a business for a local startup company to design and to commercialize this type of aquaculture farming in the Lake Victoria region, but could be also in other regions as well. So it's not specifically meant for the Lake Victoria region. However, again, in terms of the economic viability, there's a lot to do, and we need to see. It also depends on the particular region. Do we need always an MBR? How about the PV system, the size of the system? We still have to study about the degree of autonomy and the economic side of the entire project. This is still, as Kira mentioned, this is our homework we have to do. We have to write our final reports, and after having done this, after having analyzed, we can see how to step further. But definitely, this is one of the visions to make business with this type of systems in this region.
But in general, I think also one, I mean, you mentioned it, that it's a modular approach, so you can kind of use various parts of the project with various applications, right?
Yeah, and you can adapt it to the requirements of the local people. So you don't need this as we have it. So so at the moment, one of the first result findings, I think PV is very good because it's rich in sun, it's running smoothly, and with the biogas it might be difficult because you always rely on a supplier. If you have no agriculture waste, or so some people provide agriculture waste, and if they realize that you need it, they charge, and the price might be growing up. And so it could be good if you had a farm, if you had anyhow a waste which needs to be disposed something, and if you had an aquaculture next to the farm, it's wonderful. But if you rely completely on the bio-waste from others, it could be difficult due to this dependency, since you depend on this. So, and sun is always rich, and it's for free.
Yeah.
Just one short remark.
Okay, thank you. So there is one more question which just came in, which we are also trying to answer. Is it possible to do various vegetable cultures using Wrasse with aquaponics or aquaponics? Yeah.
So Kira?
Yeah.
You have some aquaponics or aquaponics.
So aquaponics normally combines aquaculture and hydroponics. So this is soilless vegetable culture, which of course can be done. However, you need people who know about hydroponics and about Wrasse, which are both like quite hard to do. For me, I wouldn't recommend it. I would recommend to do it how we do it in VicInAqua. Just use the effluent of the Wrasse in vegetable production and not reuse it in plants and then back to the fish, because both vegetables and fish, they need a different quality of water. They different, like the plants need much more nutrients. You can use the fish nutrients that they in the effluent, but then it's not balanced to what the plants need. So you will need to add additional nutrients. So in this case, I would go for a decoupled aquaponics. So we have basically two loops, and then you use the Wrasse in the middle, mineralize the water, and then bring it to the plants. But this is a whole other technology, I would say.
Yeah, so maybe something for a project in the future to do a little bit more research on. Yeah, okay, so I would like to close the webinar for today. First of all, I would like to thank you, all the participants, for your interest in the VicInAqua project, for participating in the webinar, and for coming here, questioning all the questions. And so I would also like to thank you, Jan and Kira, for giving the presentations as well as answering all the questions.
Thank you. It was my pleasure.
So thank you very much. If you would like to stay in touch with us, we have a website, which is www.vicinaqua.eu. There you find also some more information about the project, some more details. You can find our contact details. So if you have any further questions, you can just contact us and we will come back to you as soon as possible. So yeah, thank you very much for your time, for your interest, and yeah, I want to wish you a good day. So
bye-bye.
Goodbye. Thank you.
Bye. Thank you, Karsten. Bye.
Bye.